Newton's gravitational law, published in 1687, grew out of his study of Kepler's laws. Kepler, using the radical idea that planets rotate around the Sun rather than around the Earth, gave up the idea that orbits were circular. Kepler's first law states that planets move in elliptical orbits with the Sun at one focal point. Note the terms used to describe a planet's closest and most distant approach to the Sun. Kepler's second law states that during the same time interval, the areas a planet sweeps out from the Sun are equal. The time it takes for a planet to complete its orbit is called its period, and is given by the symbol capital T. Kepler's third law relates the period to 1/2 of the major axis of the orbit. Here, c is a constant. Newton realized that the force on an apple and the force on the moon are the same. Any two objects that have mass experience a gravitational force that varies as the inverse square of their separation. Kappa G is a constant. Since gravity is a conservative force with a simple mathematical form, we can easily find the potential energy. As two objects move away to infinity, the potential energy goes to zero. The total energy of an orbiting object is given by the sum of the kinetic and potential energies. The escape speed is the speed that allows an object to just go into orbit and escape the Earth's gravitational field. This occurs for an object of mass m when the total energy is equal to zero. Hyperbolic orbits never close. This type of orbit exists when the total energy is positive. When the total energy is zero, the hyperbolic orbit closes to give a parabolic orbit, and at the furthest point from the focal point, the object comes essentially to rest. When the energy is negative, the radius is restricted due to the fact that the velocity squared must be a positive number. Such orbits are either circular or elliptical. In fact, due to the center of mass being displaced from the Sun itself follows a small orbit. This is seen as a small wobble in the Sun's motion. This wobble can be calculated using the lever law. The effect of the Earth on the Sun is extremely small. Newton's law, like many such laws, has an unsatisfactory aspect, which is, how does one object know the other object is there? Newton's law implies that if we suddenly change the mass of one object, it is instantaneously felt by the other object. This principle is called action at a distance. A better description is to assume that there is a gravitational field around a massive object. This produces a vector quantity that points to the center of mass of the object. A small test particle would feel a gravitational force which depends upon where it is located within the gravitational field.